Now this time, suppose we have a H prime again, the perturbing Hamiltonian, which I'll again decompose into two pieces. Okay, so V of r and a cosine omega t, but we'll do the same type of approximation that we did earlier. So we are again going to start with CA at time equal to 0 equal to 1, CB at time equal to 0 equal to 0, and we are interested in how the CB is going to change. So remember, we have our first order perturbation theory equation, which looks like 1 over I h bar starting from some time to present time. Okay, so what I will do is I'll start my oscillation, okay, at time equal to 0. So our h prime is going to be something which is going to be constant, and then it will start oscillating at time equal to 0. Okay, so this is a function of time. So it's 0 until it reaches t equal to 0, and then it starts oscillating. So my CB at 0 is 0. So I integrate from 0 to t of h, remember what, b a prime, e to the I, which way does it go? Plus or minus omega 0? Plus. Omega 0 t prime, hba of t prime, d t prime. Okay? So it will look something like this: 1 over I h bar, 0 to t, that's V of r. Okay, so the matrix element between B and A, and I have here a cosine omega t. Again, let me be consistent. Let me make this big omega. Okay, so that's the frequency that I am applying. Okay, that's my perturbation. T prime e to the I omega 0 t prime dt prime. Now this is approximate. Okay, first order perturbation theory. What's VBA? So suppose I am putting my particle inside an electric field. Okay, so suppose that my V of r, okay, looks something like this. Okay, I have an electric field in some part of space. So the electric field is polarized in some direction. Okay, so that's the direction of the electric field, and has some magnitude, E0, and oscillating with cosine omega t, capital omega t. All right. Now, the particle that I have in my system has some charge E, so the H prime associated with this electric field is going to be, okay, how do I write the energy? Minus E dot the polarization vector associated with it. Okay, so it's going to be minus E dot, okay, electric field times r, charge is negative, electron. So I have something like that. So it's going to be E dot r, okay, times the charge. Okay, so this thing we are going to call the P, okay, so E dot P, okay, so effectively what we have done is we have absorbed this E into the dipole moment. So I should really make this a different kind of symbol. Okay, your textbook uses this curly P, but effectively what this is just E times R. So this VBA is just so H prime. I'm sorry, I'm getting a little tired. Yes.
Are we now solving for a hydrogen-like system?
Well, it could be three-dimensional, yes. So H0, we don't know what it is at this system, at this point. Okay, so this is my V. Okay, the time dependence I have taken out. Okay, so I have something which looks like this. Okay, and therefore what I have here for VBA is just E dot this P, the matrix element associated with PBA. Okay, so what is PBA? I'm opening too many parentheses, but I hope this will be clear. It is B times this E times R times A. Okay, so if it's a vector, then that's a vector, obviously. Okay, so I have some dipole moment associated with the system. It's inside the electric field, and I'm going to put in a 1/2 e to the I omega t prime plus e to the minus I omega t prime and e to the I omega 0 t prime dt prime. So we'll make the same approximation. Okay, 2 plus omegas coming together are going to be too fast to make any contribution. So I'm going to just pull that away. Okay, so basically this is what I have. Okay, so this P is called polarization, but it's just the expectation value of charge times the position of the particle. All right. So what does that give me? That gives me 1/I h bar. Electric field, magnitude of the electric field. Let me call it E0 because I called it E0 over there. And PBA, which is, okay, again, the matrix element associated with V. Okay. And then I have 1/2, so let me pull that 2 over there. And the integral of e to the I omega 0 minus omega from 0 to t. So that's, again, an easy integral. It's going to be e to the I omega 0 minus omega. You see this factor appearing here again. The upper limit is t. The lower limit is 0, so minus 1. But I have to divide this by the coefficient of t, so it's going to be omega 0 minus omega. Okay. Now, what we do, okay, I'm really interested in, okay, this is just, I'm sorry, I'm working very disorganized way. VOR is discussed over there. This is my CB. Okay. So, what I need is going to be the magnitude squared of this. And whenever you have a term like this, e to the something minus 1, it becomes very useful to factor out part of the exponential. Okay, so I have 1 over I h bar E0 PBA, and then I'm going to take out half of this, so e to the I omega 0 minus omega times t over 2, okay, divided by I omega 0 minus omega. Now if I factor half of that out, what am I left with? E to the I omega 0 minus omega t minus e to the minus I omega 0 minus omega t.
I think we should have over 2's.
Yes, and we should have 2 over 2's over 2, okay, like this. So now I can write this as 2I sine omega 0 minus omega t over 2. Okay, now let's see what we can do for magnitude of CV. Maybe I'll do it over here so that we can compare the two results. Okay, so okay, so what happens to CB magnitude squared? Okay, I have a bunch of terms here there, but the two i's are going to cancel. So I have E0 PBA magnitude squared. So I get squared magnitudes of those things. Then I have a two i's cancel, so I have an h bar squared. Okay, and I have a sine squared omega minus omega 0 over 2 times t divided by omega minus omega 0 squared. Okay, so now you see we get something which is very similar, right, to what we had over there. This object is oscillating with omega r, and omega r is where? Okay, right over here. Okay, so there is some difference between omega r and omega minus omega 0. So the difference is this term. So if that term is small, okay, indeed if the perturbation is small, then the oscillation frequencies of these things are quite close to one another. But remember, that's an exact result, whereas this is first order perturbation theory.
But so also in the exact result we have large omega minus omega 0 squared, but in this one we only have omega minus omega 0.
Yeah, but that's because of my fault, right? That's omega minus omega 0. There's no small omega in this problem.
And about square?
Which square?
I mean, in the omega r, we have large omega minus omega 0 squared. And in the approximation, we have omega minus omega 0.
I think that's also my fault because in omega r we have a square root here. Okay, so eventually by cross-checking all of these things we are going to get the correct equations. Okay, in any case, they are very similar. Okay, so let's just go on with this. Now, what is this saying? We have something here which let's try to plot this. Now, so if I just try to plot this as a function of the frequency that we are applying as a perturbation, okay, and over here I have something, okay, so let me just write this piece. So sine squared omega minus omega 0 over 2t divided by omega minus omega 0 squared. You see, this is going to be small unless my omega is again around omega 0. Okay, so just like the exact solution, I am going to get a maximum when this capital omega is equal to omega 0. And what am I going to get as a result of this, okay, expression when omega is equal to omega 0? Well, I have to expand this sign near omega equal to omega 0, which is going to give me t over 2 times this thing squared. So those are going to cancel. So I'm going to get, okay, t squared over 4, right? But at other points, it's going to decay. So it's a sine squared function. It's always going to be positive. So I'm going to get something which looks like this. Now, as time becomes larger and larger, you see this gets squeezed in. Because this point here, okay, corresponds to the case when omega minus omega 0 over 2 times t is equal to pi over 2, right? When that's equal to that, then sine pi over 2 is 0. So that tells me that omega minus omega 0 is equal to, cancel the 2's, pi over t. Okay, so this distance here is equal to pi over t. Okay, so you see what is happening here. As time increases, the probability of transition increases. Okay, so the probability of transition increases, but also the selectivity of the system to the frequency also increases. You cannot be too far off from omega 0. Otherwise, you are going to get 0 transition probability. Okay? So what type of function is this? Okay, you see, as I increase t more and more, it's going to be steeper and steeper, and it's going to, okay, do something like this. Okay? So if the area under it is constant, it's a good candidate for a delta function. Okay? So let's see what the area under this function is as a function of omega. So if I look at what sine squared omega minus omega 0 over 2 times t divided by omega minus omega 0 squared d omega is. So if I just try to find the area under this curve, Okay. What do I find? I'm going to get, okay, so let me make a change of variables. Let me call omega minus omega 0 times t over 2 as x. Okay, so that's going to be sine x squared. Then I'm going to get minus infinity to infinity sine squared x.
So why did we create the 0 point as pi over 2? Shouldn't it be pi?
Sine
Because
pi, yes, you are right. Thank you. So it's 2 pi over t. Okay. So I have that, and then for the denominator, I'm going to put 4 over t squared times x squared. And for d omega, I am going to put 2 over t times dx. So it will be t over 2 times minus infinity to infinity sine squared x divided by x squared dx. And so this is just a number. Okay. And it turns out it's equal to pi. So this becomes equal to t over 2 pi. So when t becomes very large, okay, so for very large t, you see this function here goes to a delta function times t over 2, okay, because it becomes 0 at all other places. The area under it is equal to that. Okay, so this goes to E0 squared P BA magnitude squared over h bar squared and t over 2 and the delta function of omega minus omega 0. Okay, so it means when t becomes, okay, so this is the large t limit. When t becomes large, I just select a single frequency because this becomes narrower and narrower and narrower. Okay? So in that form, it's not too useful. So what we can do is we can look at a system in which I have not a single frequency, but electromagnetic waves with large number of frequencies. Okay, so let's look at a two-level system. In a non-coherent electric field. Okay, so suppose I have some sort of cavity. Okay, and here I have my two-level system inside it. And I have electromagnetic waves of all frequencies. Okay, so I have a spectrum of frequencies here, which must be given to me. And then I am interested in what is the transition rate from one state to the other state. Okay, so you see, we already have found this change in CB to be proportional to time. Okay, so that's nice. This says that probability of being in this B state is proportional to time. That's a signature of a transition rate. So this CB magnitude squared is going to be something like the transition rate, okay, so let's call it R or something, times T. Okay, so this is going to be our transition rate. So the transition rate here, we already found something, but it's only for a certain specific frequency. Now, in reality, you never have a constant, very precise frequency, but you have a whole bunch of frequencies. Okay, so you generally have what's known as an energy density. Okay, so rho of omega is going to be some function. Okay, and we'll be using that function. So that rho of omega is the energy density in the electromagnetic field. Okay, so rho of omega, d omega, is the energy, okay, with frequency between omega and omega plus d omega. Okay, so I have some energy density here. Okay, it corresponds to lots of different types of electric field. All right, so how can I translate this discussion over there? Okay, so let's just look at it. I have this CB magnitude squared, which was given by those parameters. Okay, there's this electric field, P, H bar, etc. Now, the electric field, let me erase this, sorry. Energy density in the electric field is going to be, okay, UE, E squared over epsilon 0, 2 epsilon 0, right? Okay, so what I can do is I can, in place of that E0 squared, I can replace that with 2, way around, okay? Help me out. 1 over 2 epsilon 0 E squared, right? So it's going to be 2 UE over epsilon 0. Okay, so what I'm going to do is this energy density, I am going to replace it with rho of omega d omega. So my transition rate, okay, not transition rate, probability of being in state B is going to be 2 rho of omega divided by h bar squared epsilon 0. Okay, I still have my PBA and sine squared omega. Okay, as I get tired, I start to put things in wrong places. Sine squared omega minus omega 0 over 2 t over omega minus omega 0 squared. So now I have waves with all kinds of energies, okay, and all of them are contributing to this transition with this factor. So I want to add over all of them.
So I think the large omega in the sense would also be small.
Yes. Okay, thank you. And the omega here. Okay, but now remember that this function is very much peaked at omega equal to omega 0. Right? So this function is finite, okay, or I shouldn't say finite, okay, it's appreciable for, okay, omega is around omega 0. So you are not going to get much contribution from anywhere else. So to a very good approximation, I can just move this thing out of the integral. So this is going to be 2 rho of omega 0 divided by epsilon 0 h bar squared p BA magnitude squared, and an integral from 0 to infinity of this sine squared omega minus omega 0 over 2t divided by omega minus omega 0 squared d omega. Okay, so what did we do? We, instead of using E0 squared, which corresponds to the energy density of a wave with a definite frequency omega, we have used an energy density rho omega, okay? So this is associated with, okay, the energy density in the system. We are using this energy density times the transition rate corresponding to that particular energy. But even then, we are not relaxing it so much. We are saying, okay, I want to use the same sort of result, but I want to actually, okay, integrate over all waves with similar frequencies. So, what do we get out of this? Let's move over here. You see, this is the same type of integral that I did earlier, and it's going to give us a simple result. So we already did that integral over there. Okay. Let's see. And we got t over 2 times pi. So this CB squared is equal to 2 rho omega 0 over epsilon 0 h bar squared PBA squared, and then t over 2 times pi. Okay, so now we have a nice transition rate from the, due to these, all of these effects, when I go from state A to B. Okay, so if I write this as some rate times time, that's rate, okay, transition rate. So let me actually put it like A going to B or something. Okay, so that transition rate is going to be equal to rho of omega 0, epsilon 0, h bar squared, okay, the matrix element or the dipole moment between states A and B times pi, okay, times t. Okay, the 2's cancelled. Okay, yes?
I think the limits of the integrals are not the same. One is from minus infinity to infinity.
Yeah, but doesn't really matter. There's nothing here. Okay, so we extend those things very liberally. Okay, so this is actually called some form of Fermi's golden rule, which says that the transition rate is proportional to the transition matrix element, magnitude squared, times the density of states associated with the energy in the field. Okay, so now we can use this to test various things. For example, we can put our atom in a black box, okay, black object, okay, and then you know that in a black object, which can be modeled very well with a cavity at a certain temperature, I have all kinds of electromagnetic waves, but I know the energy density associated with it, which is the black body spectrum. So if I put my atom in there, it's also going to interact with this electromagnetic wave, and it's going to reach temperature T, right? So it will come to equilibrium with the black body radiation. So in that case, I know that probability of being in A is going to be proportional to e to the minus EA or KBT. PB is going to be proportional to e to the minus EB over KBT, properly normalized. And I can check, okay, what the transition rates between these states are so that I'm going to get these results. Okay, but that's perhaps a discussion for another day because I'm starting to make too many mistakes. So we'll meet again Friday, right? And I'll see you then.